And so this is what we wanted to do as quickly as possible. And that's why I chose a way which I thought was the quickest way to present people who don't know much about probability theory, the things which are needed, okay? And which also has this view, which we have here as taking functions of random variables and looking into function spaces and whatever. That is not so the normal view in probability theory, but it's sort of a functional analysis point of view in probability theory, okay? And functional analysis is just infinite dimensional linear algebra in some way. So I hope you all know algebra. That's why I chose this way of doing that. But I'll explain this tomorrow and the day after tomorrow, okay? Good. So now that we know how to do uncertainty quantification, we can push uncertainties through our models. Now we are ready to start looking at inverse problems in the Bayesian way, okay? So this is what this talk is about. Good, so I'll just motivate this, how we want to identify parameters, okay? And then why we do it in a stochastic way, okay? So we use stochastic or probability theory, and this is Bayes' theorem essentially, which we're using. So Bayes' theorem is connected to conditional probability and conditional expectation, and I explain the connection, okay? And we will be using very much this notion here of conditional expectation to do the updating, okay? And we'll look at two methods actually to do it, so you can quickly get up to date what these two methods are. And this is Markov chain Monte Carlo, so you can follow the numerical examples, which will be shown by Dr. Friedman later, tomorrow. And the other one is to use filters, okay? And we're going to use the simplest kind of filters in some way, and this comes from the Gauss-Markov theorem. Okay, so let's jump into the whole thing. So the whole thing is now, when we have a model, let's say like our example problem, the aquifer, and one of the things in the model is the conductivity field, but we don't know it. But we want to use the model to make predictions. So this, we have to have an estimate of what is this conductivity field, okay? So we have to in some way represent our knowledge about this unknown quantity, okay? And then when we get data, we want to be able to update, okay? So what's important here is that we use both the data, which come maybe from measurements, okay, and the mathematical model for doing the updating, because the mathematical model, of course, represents also some form of knowledge, completely differently represented, okay? So, data and from sensors and whatever, that's one form of knowledge about our system. And then people looking at big data, that's another thing which is being done. This is just looking computer programs doing something like what we saw before, this Cahoon-Loew expansion, looking through this, looking for patterns, okay? And this is what big data does, trying to see patterns, okay? And this is the Cahoon-Loew expansion was one way, by the way, of seeing patterns in randomness. Okay, so we could figure out what random variables were important and which ones were not. Okay, so mathematical or computational models represent another form of knowledge. Okay, and a very compressed form of knowledge. It's just one equation, and it tells you everything about that system. Okay, and my view on this is that this is not in competition, but if you have both of these things, they are complementary, and we should combine them. And this is what we're trying to show now on how to do this. Okay. And of course, we know it's clear, in the example I described, that knowledge may be uncertain. By the way, it may be uncertain about the computational model too, because it's only a model after all. Yeah? We left some effects away, which we neglected. Yeah? So that's the uncertainty in the model, and there's an uncertainty in the data, okay? And there's uncertainty in things which are in the model, like these parameters. Okay, good. So let me take an example from a long time ago to show you the difference between just looking at the data and building a model for that and having a computational model or a mathematical model of it, okay? And so we go back to the 16th century, on the 17th, beginning of the 17th century, okay? But it started, of course, and of course the question was how to describe the solar system, okay? And you all know that the early descriptions, they put the Earth in the center, and So what happened then, of course, the fixed stars, they had very simple movement, but there were some stars called the planets, the wanderers, which didn't have simple movements. Okay, they had very complicated movements. So the idea was to build a model to represent this data in a simpler way. Okay, and so astronomers had been doing this for actually thousands of years, you can say. Okay, and they were very capable of doing good computations, predicting eclipses of the sun and the moon and so on. Okay. And in this way was Tycho Brahe, a Danish astronomer who lived in Prague at the time I'm talking about now, okay? And he was one who had done really very, very accurate observations of the planets especially, okay? And so he had so much data, he didn't know how to actually analyze it all, and he did what you do when you have a lot of data. He hired a student helper, okay? And his student's name was Johannes Kepler. Okay, and he knew his data was really valuable. At the beginning, he was sort of not really easy giving him all the data. Okay, but then he fell ill. Okay, and he realized actually he might not live very long. So luckily, he gave all of his data to Johannes Kepler. Okay, so that's how Johannes Kepler ended up with his highly accurate and precise observations of the solar system. Okay. Good. And Johannes Kepler did, you could say, big data analysis, not 16th, but 16th century, okay, end of the 16th century, okay. And he came up with what we know as Kepler's laws, okay. And so if you remember, the first law is that the planets move around the sun in ellipses, on ellipsoidal paths, and that the sun is in one of the focal points. And so I adapting this, by the way, this little example from Miguel Ortiz. And the second law, I made a little sketch of the second law here. It's actually taken from Wikipedia, and this is the sun is here, and this is the ray from the sun to the planet. And in equal times, the ray sweeps equal areas. That's Kepler's second law, and actually we know today, which is equivalent with conservation of angular momentum. Okay, so but he didn't really understand why do they move. So, but everyone was said, "Oh, this is a really good model. It explains a lot of what we observe, and that people were able to see when the planet went behind the sun and appeared on the other side. They could compute where it appeared by knowing this, and so on." Okay, so everyone said this is a really good description and model of the data. Okay, but no one knew why are they moving on a picture. Of course, it took Newton to explain this. Okay, and of course, what he did, he made a mathematical model. So this is what he said about this. So he strove to subordinate the phenomena of nature to the laws of mathematics. So he came up with a mathematical model of gravity. Okay, and that explained how this moved. Okay, and he could compute how a light body moves around a heavy body. So this is one planet around the sun. Okay, and he could prove that this is an ellipse, yeah? If the speed is not too high. So it's actually a conic section. Okay, so in extreme case could be a circle, but none of the planets moves on circles. And it's an ellipse, and if things which come from far away. So that just, I think 2 or 3 years ago, there was some meteorite which came, people say, from outer space, from outside the solar system, went through the solar system, and out of that went into a hyperbolic path. Okay, so this is all follows law. And it was driven to perfection by Pierre-Simon Laplace, which we've seen already. He really wrote a book about celestial mechanics. Okay. And there's a little story when he presented this book to Napoleon, actually, in one of the sessions of the Academy of Science. This is like Napoleon looked into it and he said he doesn't see God mentioned anywhere in this book. And Laplace said, I didn't need this hypothesis. So he could explain everything with mathematics. Okay, good. So that's big data since 16th century, and you see the difference between just describing it and understanding what is going on. And this is the thing between having just the data and the description of the data and having a mathematical model which explains part of the data. Of course, you still need the parameters in the model, in this case, for instance, the speeds and distances and masses of the planets and the sun and so on to compute it. Okay, good. So this is big data. Big data, as I was saying before, is trying to find patterns, and it uses typically deep neural networks to do this, because that's one way of interpolating or regressing on high-dimensional data. Okay, so we'll see this later again. So something we have done too with polynomial chaos. Okay, that is often spectacularly successful, but the problem is these neural networks, when they have, for instance, they drive cars now and things like that, we don't understand them. Yeah, so it's difficult to extract insight. So that's where mathematical models are good. Good, and there's a connection of this kind of regression to Bayesian updating and conditional expectation. We'll come to that probably tomorrow. Okay, so what we're going to do goes back to these two people. So we want to update our knowledge of uncertain things. Okay, there's again Laplace, and there's Thomas Bayes. So Thomas Bayes was actually historically the first one to do something in this direction, to write down a special case of what's today called Bayes' theorem. Okay, it was published after his death by one of his friends in the Proceedings of the Royal Society in London. And by the way, the funny thing is, it is uncertain that this picture really is Bayes, but most people think it is. Okay, it's certain that this is Laplace. Yeah, they're quite certain of that. Good. So just a reminder of Bayes' theorem. It's actually very simple, and we can prove it here in 2 lines. Okay, so a conditional probability is this guy here. That's the probability of some event E by knowing that some event other information C that this is true. That's called the conditional probability. Okay, I'll give an example in a second. So for instance, let's say we're now not in one room, we're sitting here electronically, but imagine we were in one room. Okay, and I say in the next minute the door is going to open and a person is going to come in through the door. And what do you think? Well, how tall is this person going to be? Okay, then if we were all sitting in one room in Ljubljana, then you would, if you're clever, you would look at if you get it, look it up on the web somehow, the distribution of height of people who live in Ljubljana. Okay, and then you would give me the expected value of that random variable, height of person in Ljubljana. Okay, and so then the probability of being, let's say, in the range between 160 and 170 would have a certain value. Okay, that's P of E. Okay, the probability that this event occurs. Okay, this appears here. That's our prior information. Now, if we have one condition, I tell you another piece of information. I tell you, for instance, that person has high-heeled shoes on. Okay, well, now you can say, shit, if the person has high-heeled shoes on, of course, it could be a man wearing cowboy boots with a Cuban heel, okay, but it's most probably a woman. And most probably she is older than, I don't know, 12 or something like that, because when they're younger, they don't have high-heeled shoes, okay? So that's the condition, okay? Then your probability distribution changes, okay? Because now you look at women who are older than, let's say, 12 years, okay? And how is their height distribution? And then the probability of being between 160 and 70 is different than from before, where there was men and babies and everything added into the, or little children who can walk, added into the distribution. And this is this conditional probability, okay? So, and the conditional probability, if you define it mathematically, it's the probability of both of these conditions being true, okay? That it's between 160 and 170, and that it has high-heeled shoes on the person, okay? And that's, of course, is the conditional probability of between 160 and 170 on the condition that it has high shoes, times the probability that the person has high-heeled shoes on, okay? So that's the definition, actually, of this guy here. Of course, you can exchange E and C, okay? That's the probability of having high-heeled shoes on if you're in the range between 160 and 70, and you can write the same equation here. Now, on the left-hand side is the same thing, so the right-hand sides have to be equal too. And if we do this, we can derive this here, and that's what's called Bayes' theorem. So, and of course, I can do this if I can divide by PC, okay, by the probability of C. And maybe something to remember is now this here is that's called the prior information, the prior probability. That's before I knew anything about what kind of shoes the person was wearing, okay? This is the posterior. This is the probability after I know the person has shoes on, okay? And sorry, my microphone fell off. And this guy here, that's called the likelihood. That's the likelihood that the person has high-heeled shoes on, the probability, if that person is between 160 and 170, okay? And that's the probability. It's called the evidence that the probability that the person has high-heeled shoes, okay? So this is given by this expression here. So this here is changed by this factor here, okay? Okay, now there may be a case that there's no updating, that this is equal to this. Yeah, for instance, this is equal to this. And this happens if this, the likelihood is just the probability of C, because then of this course factor becomes 1 and nothing is changed, okay? And this really means that these two events are independent, okay? In other words, the probability of this, both of them being true, is just the product of these two, yeah? P of C is here, and the PEC is just PE here, okay? So this is like, for instance, if the condition was something completely different, completely unrelated to heights of people. If I said you want to know the height between the probability of being 160 and 170, and as condition I tell you the sun is shining outside. Well, it has obviously nothing to do with the height. It will not change the probabilities, okay? This would be independent. So that is not a very useful information. It is independent of what we want to know. It contains no information, okay? But if it does, then this factor is different from 1, and then it changes the probability. So, and this is a very, very important theorem in probability theory. And Sir Harold Jeffreys, a famous statistician, says that Bayes' theorem is to the theory of probability what Pythagoras' theorem is to geometry. And we'll see this is literally true later, okay? Good. So now it's how does Bayesian inference work, okay? So we know I have knowledge about some event E, but we cannot observe this event directly, okay? So this is like, we don't know how high is this person, how tall is this person, which is going to come into the room. Okay, we cannot observe it. But someone has told us another information, for instance, about the person has high-heeled shoes on. Okay, and so now we have to make our knowledge, which we have here before. This was the distribution, how tall are all the people in Ljubljana. Now I have to make it consistent with this new information. So I can exclude little babies, they don't wear high-heeled shoes, everyone younger maybe than 12 years, maybe everyone older than 90 years, I don't know, so it makes a different distribution, okay. Then you can exclude most of the men, okay. You can also include all the women who wear flat shoes, okay. So very, very tall women may wear flat shoes and not high-heeled shoes. And that leaves you with the rest. Okay, and that probability now being between 160 and 170 is different with it. You know? But we want to change the probability to reflect this. So it has to become consistent with this new information. And we don't want a contradiction between these two things. So the idea is to change our model. So this is our P of E by so much that it becomes consistent. And this is what Bayes' theorem does. Okay. So, and to do this, we have to predict with our present knowledge or model the probability of all possible observations and compare the actual one. You can see this here, and this is actually in the likelihood. By assuming that the person is between 160 and 70, I have to predict what is the probability that the person has high-heeled shoes on. Okay. So now for shoes and heels and whatever, and tallness of people, this would be some kind of statistic where you use this from. But here we'll have our mathematical model to do that. Okay. So we have to do a lot of computations to compute this likelihood. That's what it comes down. That's why it's a very compute-intensive thing what we're doing here. Good. So let's go back to our model inverse problem. I've changed it a little bit. I added a term depending on time too. So this can be time function now. So this is how it changes in time. Okay. And we want to not want. So uncertain is the conductivity. Again, we take as the log of the conductivity because the conductivity has to be positive. I always can take the log. The second law of thermodynamics requires the conductivity to be positive. So that's why I can take the log. And I want to know the state U of t, and maybe the initial condition is uncertain or unknown, okay? And I make observations. These are my quantities of interest. And then I want to predict, to figure out what is kappa and what is U0. Okay. By the way, that's something which is being done in weather prediction all the time, okay? So they don't know what the state of the atmosphere is at every point on the Earth's surface when they do this, but they assume something, but it's uncertain what they assume, okay? So they know there's uncertainty in the initial conditions. There's also uncertainty in their model of the atmosphere, okay? Then the weather people, they run the model, let's say for the next 24 hours, and they will predict what the weather will be in 24 hours. But what they do today, they predict a probability distribution because they know the input, the initial conditions, was uncertain. Okay, they only have data from the meteorological stations. In between, they have to make an educated guess. And this educated guess, of course, has an uncertainty with it. So they predicted the weather tomorrow, then they measure the weather tomorrow, okay? But it's, of course, not exactly what they predicted. Okay, because they predicted a probability distribution, and they now take the measured values and update their model, okay, of the state of the atmosphere to do the next prediction. So something of that kind you can think of doing for this aquifer. Okay, you want to predict the state, that is in this case the pressure distribution of the fluid in there, and you want to also find out a property of this here. That's not what's done in weather prediction, but here we want to find out what is this kappa. Okay. Good, so this is one possible realization of such a kappa, assuming that it's scalar. As I said before, if you really have a random field, here you would expect that it's not isotropic, so that it's a little tensor, okay, at each point. Good, so now this is where you would measure, okay, so in this case here with a reservoir, you send out your doctoral students and let them drill holes. Everywhere there's a blue dot, there's a hole being drilled. Okay, there's 10, 120. Here you have a whole lecture hole sending out all drill holes. Everywhere where there's a blue dot, there's a hole, and they measure U or kappa or both. Okay, and then we see how when we do Bayesian updating, is showing the result right away. So what happens? So of course, if you only have 10 points, that's quite coarse. And so this is the error you have in describing kappa, okay? So here the error is practically 1, okay? Then after one update, it drops down to 10%, okay? And that's where it stays with 10 points. So it's a residual uncertainty left about, I don't know, 8% or something like that, which you cannot resolve because you don't have enough information, okay? Now, if you increase the number of points, you can see, I get a better and better and better results. So for 450 or 447 exactly here, you get, I don't know, down to 2 or 3%. Yeah, that's a logarithmic scale. So this is somewhere 2 or 3 here. Okay, so you can identify the random field up to 2% or 3% accuracy, the kappa field. Okay, and this is what it looks like at one point in the field. So at this point, because we did everything in the computer, we know what the true value is. The true value was 2 here. Okay, and this was the prior distribution, okay, and this is the posterior after we've done the Bayesian updating. So you see how it's become narrow, sharper. That means we have more certainty that this is close to here, and it's centered at the true value. Good. So what is it? Just to repeat once more, what's the general idea? We observe a system whose structure we know in principle. We know what equations govern the system, okay? But the behavior depends on some quantities which we don't know, and they are uncertain. Okay, we model our uncertainty now in a probabilistic way. This is the Bayesian setting. So we take a probability distribution on these parameters. So we take a random field for kappa, and this randomness reflects our uncertainty. Okay. And by the way, taking of conductivity fields for aquifers, this is completely. You go to a geologist or geotechnical engineer. They're used in thinking of probabilities for these kind of things, okay? And now we perform a measurement and observation, okay? And then we update our knowledge. And that's the identification. And for this updating, we use conditional probabilities from Bayes' theorem, okay? And repeated measurements, as we saw here, lead to better. So this is the first measurement, and that's the second one will lead to better identification. So the error drops here from 8% to, I don't know, 3% or something like that. Yeah, good. And if the system is, by the way, something which is changing in time, like I had indicated here, sorry, then of course you might want to know the state at time t, which is also uncertain. So you want to identify that one as well. Okay, good. And by the way, for instance, this is something which happens, so let me stay here. For instance, this is what happens, for instance, all the time when you fly in a plane, okay, and the pilot then, the human pilot, puts the plane on autopilot. So what is autopilot? Autopilot is some electronics, okay, which is trying to keep the course and altitude and speed, okay. So what does this autopilot do? It measures the state of the airplane. How fast is it flying? What's the altitude? What's the position? What's the course? Okay, it measures this and compares this where it should be, okay. By measuring it, though, it has measurement errors or whatever. So this is a Bayesian identification of the state of the plane. And it takes then the expected value of that identification to change maybe the thrust or the height or whatever to stay where it should be. Okay. So this is this filtering which happens all the time continuously, and it's updating in a Bayesian way, simple Bayesian way. We'll see the state of the airplane. Okay. Good. So now we want to model this with probability. We've seen this already. I've talked about probability before, so we can go here quickly. It's a mathematical concept, and we have to match it to something in the real world. Okay. It's clear that this applies to aleatoric phenomena, which are truly random in some way. Okay, like turbulence of a fluid or something like that, or frequencies of occurrence or something like that. Okay, this is the Bernoulli's law of large numbers. Okay, but we'll apply it here also to epistemic concept, like the thing we had here. Okay, so we don't know. If we have an aquifer, the conductivity has a certain value, but we don't know it. So the uncertainty is in our knowledge. Okay, and it has to be an extension. I talked about this before, Aristotelian logic. Okay, to uncertain propositions. Okay, and this is the realm of Bayesian methods, and that's where we're going. Okay, if you look at how probability theory started, and especially what Laplace did, they applied probability, and Bernoulli's too, they applied probability concepts to epistemic and aleatoric phenomena. Okay, good. So what is the mathematical formulation of our model? We write it now as something like this. Okay, so that's a stochastic differential equation. Okay, so you can say, why don't you write divide by dt and have what you had before? And why I don't divide by dt is the following, because I added some noise term here. That's white noise here. And the dw dt actually does not exist. So that's why it's written like this here in differentials. Okay. The differential of u plus a, that's the operator governing the physics of the problem. This is sort of the deterministic input to the system, rivers, rain, or whatever, and that's some random thing because there's errors in the model, okay, or errors in this here. Okay, so we have some random thing changing the state of the system. So that's why the state of the system becomes uncertain. Okay, even if I know q, it's uncertain because of this term. Okay, so this is some noise. And q are the unknown parameters. And now we assume that for a given q, g, or whatever initial condition is a well-posed problem. So it gives a unique solution. So it means we have a solution operator, which takes the initial conditions, the q and the g and the noise, and gives us a new state at time t, depending on q. Okay. So now for identification, we'll use something which I call the extended state. We take u, the state of the system, so to speak, and the thing we don't know, the q, and put it into this here, into a new space x, which is the product of these two spaces. Okay, so this is the thing I want to identify. And I have a way of examining for knowing this thing here at time t n minus 1 to 1 like this. So the u is advanced this way, and the q will be advanced with our identification methods. Okay. So we can write Cn is a function of what was at time t n minus 1. So that's the deterministic thing going now, instead of a differential equation, now we have a difference equation which just looks at discrete moments Tn in time, okay? We just look at the moments when we observe the system. That's the only thing which is interesting. Of course, this applies also to the stationary case where there's different g's, which are the different times, so to speak. Good. And now we may have to make a mathematical model of the observation. We've seen this already. So before, this is one of our quantities of interest. Okay, so that's something which depends on the state and Q, so it depends on the extended state. Okay. And we assume that this observation, this eta n, is also noisy. And the noisy observation we call yn, and the yn is now this here. It's a function of this guy here and some noise of observation. So this is some little function h of xi of this extended state and the noise. Okay. So we know now, having xi and the extended state, we can predict what the observation is in a probabilistic sense, because this is a random variable. What we really want now, the inverse problem, is we want the opposite. We want, knowing eta, that's the observation, not just the probability of it, but the observation. We want to know what is Q. Okay, so if we look at this just as a function of Q, then this function, unfortunately, is not invertible, but this is what we want. So it's not invertible, and that's why this inverse problem is an ill-posed problem. You want a function which gives you Q in terms of eta, but such a function does not exist. Okay. Typically, the reason is that the measurement does not contain enough information. Yeah. Good. So we model everything now as random variables. Okay, so this is formally by putting these guys into tensor product spaces, where this is the original deterministic space. This is a space of random variables, which we had before. Okay. So, and then we are in a Bayesian setting now. So I model the initial state, u0, and the Q, the parameters, means the extended state, xi, I model is as a random variable, okay? And then I can update the information about this here. And then the problem becomes a well-posed problem, it turns out, this inverse problem. But it gives me less information. It doesn't give me the exact value Q, it gives me a probability distribution. Okay. Good. So what is this mathematical formulation of filtering? So what we're doing is some filtering. So we want to track this extended state, xn, okay? So we replace this, as I said before, by a random variable. I call this random variable xn. So this random variable is supposed to track this thing here, which I cannot observe, okay? I know it exists in my model, but I cannot observe it directly. And the way I want to track it is through these observations. So I call that with a little hat. So y hat is the observation at, y hat n is the observation at point n. Okay, so we have a prediction of the state now as a random variable with the same model. Okay, you just plug in a random variable, out comes a random variable, and this is the noise in the model. So I get a new random variable. That's the forecast. That's why there's a little f here. That's the weather forecast. Then the n would be, let's say, 24 hours. So every Tn is every 24 hours in this case, okay, with weather forecast. So xn is the state of the atmosphere tomorrow, okay? Then tomorrow, and they forecast the observation. They forecast what the weather is, or temperature, wind speed, or whatever is going to be at the meteorological station. So that's what is this here, okay? And now they observe it, what it is. But then they have to now combine this observation with what they predicted. And that's called assimilation. They assimilate the data. That is lingo from the meteorologist. They assimilate the data into the model. And this is through a mapping here. So it takes the forecast measurement, and the actual measurement, and a function of that, and it changes this random variable to this one. Okay, and that's the assimilated random variable. And we'll put a little a there. So it's not there yet, but here you can see it. So we call this x sub a later on. Okay, the assimilated random variable. And hopefully this is in some way similar to this here. Of course, this is a random variable. This is a deterministic thing, okay? But we still have to determine what is this update map. And this change here, that's what you call the innovation. That's what's the change due to this observation, okay? Innovation, so we have new information, and that's why this is called the information. So we just concentrate now on one step, going from n-1 to n, okay? So we can drop the index n, okay? And then it looks like this here. So we have the forecast, and which is the information, which takes the forecast state, the forecast observation, and the actual observation, and gives me a new random variable. Okay, and this random variable hopefully has the distribution which is given by Bayes' theorem. Okay, that's the idea. Good. So the schematic representation is like this. You have a model, you predict what the state is and what the quantity of interest is, the observations. Then you actually do the inverse, and then you do the inverse problem and update it, and then go through the cycle again to do new observations. Okay. Good. So sequentially, it's done like this. That was the start of my distribution, let's say, of what kappa is. Then I do a first update. It changes like this. Then I do another experiment in this case. So one flow is this in direction. Now let something flow in this direction. I do another update and so on. Okay. So this is now the time is just the different experiments I do on this aquifer in this example. Okay. Good. So what is the setting for the updating? So the prior knowledge is also called the forecast, and it's a random variable in the space U. Okay, and the extended state is the random variable in this state here, and the measurement is a random variable, the predicted measurement, which depends on the forecast and some error, is a random variable in this state. Now we perform an observation, and we have to compare it to this random variable, and that's what we do by Bayes' theorem. Okay, it gives the probability distribution, though, only of this new assimilated state. Okay, and this is the basis for Monte Carlo methods, Markov chain Monte Carlo. Another approach are these filters where this mapping C's are determined or approximated. We'll come to that later. So we'll look at this first and then at this. Okay, good. So now we want to use Bayes' theorem. I've written it now for this here. So I is the information we'd like to have about the extended state. M is the measurement information, okay? And then this is Bayes' theorem as we've seen it before. So this is our prior before we measure, and it changes through likelihood divided by evidence to the posterior. Okay. It comes a little problem now, and the little problem comes if the probability of observing y, now our y is just a real number, what we observe, okay? And unfortunately, when we have this kind of discontinuous distribution, one real number cannot have a non-zero probability. So it turns out that this condition will be violated in many cases, okay? So you see now, of course, when you have to have now 0 divided by 0 here to do the updating, and that becomes a problem, okay? The problem is we'll probably have to do a limit somehow how Pm of y goes to 0, okay? And this is actually something which has plagued probability theory for quite a while. It's called the Kolmogorov paradoxon. Okay, you can look it up in Wikipedia. It's described there. Okay, and this is when this probability is 0. So we have to do this limit in some way. The problem is that the limit can be done in different ways, and this is where this paradoxon came from. Okay, I will not explain it now. You can look it up. There's one way where you can do this limit, and this is when there is a joint density of these variables x and y. So if there's a joint density, then you can do this. You can write the joint density divided by this guy here, which is a marginal density. That's the posterior density, which you get if you were to observe y. Okay, and this marginal density here, this guy here, is just the integral of this joint density over the variable x. So we integrate out the variable x, and what's left is this guy here. That's sometimes or often abbreviated zy, and z is for the German word Zustandssumme, because that's the sum of the states. Okay, so in physics, these are the states, all the x's, all the x's, and that's a sum, integral over all the states. Okay, so it's the sum of the states here. Zustandssumme, that's why z. Good. So we'll try and we'll assume now that there is a joint density, and then you can rewrite by the way, the joint density can be rewritten like this, in the prior density and in the likelihood. Okay, that's the density of observing y if x were true. Good. And by the way, this zy is necessary to make this in the probability density, so it integrates to 1, obviously, yeah? And because the state, if the space state is a high-dimensional state, then this is a high-dimensional integral. And to compute this is a problem. It's a numerical problem to compute this. Good. So now we look at Markov chain Monte Carlo, and Markov chain Monte Carlo is the following idea. Okay. You start with a prior density, and on this space of states, you simulate a Markov chain. So what is a Markov chain? A Markov chain is a sequence of points in this set of states, okay, where there is, when you're sitting at one point, the next point depends only on the points where you're sitting. So that's the Markov property. The probability of going to another point depends only on where you're sitting now, on the state right now. So if the transition probability depends on the state, only on the state, this is called a Markov chain. Okay, after a Russian mathematician, Markov. Good. And we construct a Markov chain which has a stationary distribution. So a Markov chain which sort of samples a stationary state. Okay, and we'll construct one so that the stationary distribution is the desired posterior. And it's actually quite simple to do so. And this is called the Metropolis algorithm. It's a special kind of Markov chain Monte Carlo algorithm. So you observe y hat, yeah, and now you want to do the update. You want to compute the conditional probability of x given y hat. So you're going to compute this guy here for y hat. That's what you want. So you start with an arbitrary state, which you pick from the prior distribution. It has to be so that the density there is larger than 0. Maybe by telling this here, I should say something. I might write it down in one of the further slides. There's something called Cromwell's rule, okay? And this is it. If you want to identify something, Cromwell famously wrote a letter. So Cromwell, remember, was someone who ruled England in the 1600s, and they actually killed the king, beheaded him, and England was a republic for a short time. Okay, and but it was only a short time, and the monarchy came back, and it's up there from then up to now. Okay, so but what that's also, there was the time in history when there was the Reformation movement. Okay. So, and there was many religious discussions, and he wrote to a church body in Scotland. He wrote, "By the bowels of Christ, I beseech you, consider the possibility that you might be mistaken." And this is taken as Cromwell's rule for Bayesian updating. It means the following: even if you think some states will not occur, don't make the probability for them, the prior probability for them, 0. Because if you do that, then no amount of data can lead you there. Because if you look here at this theorem here, okay, so if the prior probability for some x is 0, then this has to be 0, no matter what this factor is here. Okay, so no amount of observation will lead you to a non-zero probability if you start with a 0, 1. So if something is possible, you should give it a non-zero probability so that the data can lead you there if it has to be. Okay. Good. So now you pick one state here, x0, and it's going to be a sample of the posterior distribution. This is x's with indices up there to the left, and you pick it where so that probability is non-zero. Okay. And what you do then, you compute this likelihood times prior. Okay. And call this rho c. Then you make a move. You want to move from x0, okay, from c, which is x0. C is now not the state, but it's just c is this where we're sitting in the Markov chain. It's not the exact state what it was before. And you draw this a random zeta from a proposal distribution, which is conditioned at sitting at c. Typically, it's something in the difference between x and c. This proposal distribution has to consider all the constraints which are on the state. It should not propose something which is impossible, okay, or where the probability here is 0, okay. So you take, there's a proposal distribution. Often this is a Gaussian or something looking like a truncated Gaussian, okay. So with higher probability, you don't move so far, Okay, and then you look at this factor. What does it look at this new point here? Okay, and now you compare. See, if you want to go to the posterior, here we have it. If you want to go to posterior, you want this thing to get large. So you got the sample from the posterior. You want this factor here to become large. So what you look at is at the ratio of this to this here. Okay, so that's this ratio here, rho zeta divided by rho c. And by that way, by the way, we've cut out to have to compute zy. It's not necessary because it cancels out from this ratio. Yeah, it's for the same y hat. So the z y hat cancels out. We don't need it. Okay? So we have this ratio. So if this ratio is larger than 1, of course, then this factor is higher at the new state. So this is larger than this one, okay? Then you should move there, okay? So you compute this number alpha, which is the minimum of 1 and this here. So if this is larger than 1, we get 1 here. And if it's smaller than 1, we get something between 0 and 1, okay? And now we take this alpha as a probability to accept the new state. So what you do here, you take a uniformly distributed random variable and look, is it larger or smaller than alpha? And then with probability alpha, you accept the new state. So you only move if this new random variable, which you've chosen here to check this here, is another Monte Carlo trial, if it's larger than alpha. If it's larger than alpha, you move. You have a new state. Yeah. So you've moved from state 0 to state 1 and so on. And then you just repeat it and you get more and more xk's. Okay. And after a certain while, a so-called burn-in period, the states will sample, there will be samples from the posterior distribution, okay? Now, I will not prove this here, I will just leave it like this. So this is how the Markov chain Monte Carlo works. So what's nice here is that it's absolutely simple, okay? Good. So that's the nice thing. So it's very easy to write down. You see already where it's becoming expensive is when you compute these guys here. Yeah? Now you have to compute what is the probability density for y hat given a certain state c. Okay? That's where you're sitting right now. Okay? And every time you compute this, you have to go into your mathematical model and solve the PDE for the active fair ones, or do a one-weather prediction or whatever. Okay? So computing these rows, rho c and rho zeta, is very expensive. Even more expensive is computing the zy, the Zustandssumme, but we don't have to do it here because in the ratio it cancels out. Good. So now this is a 2D sketch of how this works. Okay, this may be the posterior distributions. These are the marginal distribution. So the state now, the x now has only two coordinates, x1 and x2. And you can think of the red guys being samples of this Markov chain. Okay, so they go there, they're driven there where the posterior is high. Yeah, that's because they're driven where this factor is high, and this is proportional to the posterior. Okay, good. So once the Markov chain becomes stationary, this is the sample from the posterior because the posterior is proportional to this here. This is this Zustandssumme, which is the proportionality factor, but we don't need it in the Markov chain Monte Carlo we've seen there, and that's a nice thing there. Okay, it's a very simple, that's a nice thing, but it's a Monte Carlo method, it's a probabilistic method, okay? Problem being with a probabilistic method, for instance, you would not want to use this for an autopilot in the plane, okay? Because it can have the probability of being completely off. Not for a long time, but for some draws it can be completely off, and that you don't want to happen in the plane. So you probably would not take a probabilistic method to be the algorithm for your autopilot. Okay, that's one of the problems. The other one, that it's a Monte Carlo method and that makes it slow. Okay. Another problem is that the sample is not independent. In fact, they're correlated. Okay, because there's a correlation between xk and xk plus 1. They come from a Markov chain. And they're only asymptotically stationary, so you have to wait for the burn-in, but you don't know how long the burn-in is and so on. So these are all difficulties. Okay. And the thing, I'll show an example of that here. If the prior and the likelihood are very different, or the prior and the posterior are very different, then it can take a very long time. This acceptance ratio may be very, very slow in the step 4. Yeah? So imagine this acceptance ratio is 10 to the minus 13. Yeah? Then you have to do 10 to the 13 doors here to get there, to make one move. Yeah? So although you can show that this Markov chain will converge to the posterior eventually, yeah, with probability 1, it can take a very long time in this case here to get there. So if you make estimates, it can take several times the age of the universe to actually get there. So then it's clearly not very useful. You don't want to wait that long. Okay. Good. So that's why we turn to conditional probability and filtering. Okay. And we've seen the conditional probability builds on this, we'll see this, it builds on the conditional measure. This is what some people have said about this Kolmogorov-Borel paradoxon, which you can look up in Wikipedia. Okay, if we have a conditional probability measure, then we can compute the conditional expectation as just the integral with this conditional probability measure. Okay. Now Kolmogorov, who was the one to formalize probability theory, he recognized that this does not work very well, especially in cases where it's very difficult to define this thing. Now, this is when my has probability measure 0. So he turned things around. He said, I will define what is conditional expectation. When we have this operator, then we can define what is conditional probability, because that's very easy. We've done this already. Yeah, we just take a random variable, which is 1 on the set we would like to know the probability of, and 0 otherwise. So if we can compute this here, we have the probability, and we have this posterior probability. Okay, and this is easy to show that this, what he just defined, that this agrees with what is conditionally, what comes out of Bayes' theorem. So when this is non-zero probability, and otherwise it's taken. This is taken now as the definition of updating, of conditioning. Okay, so what is conditional expectation? We have to define what that is. So if we have a random variable, the normal expectation was defined as a functional, mapping the random variable into the reals. But we can also see this as an orthogonal projection, and I will take the same symbol for this new thing here, which maps this random variable onto the random variables which are constants. Okay. So what does it do? It just takes this number times this random variable, which is constant. So it maps this onto a constant random variable. Okay. And it turns out that this space here is orthogonal in the inner product we have to this space with the expected value 0. So you can view the normal expectation as an orthogonal projection from this space onto this one-dimensional subspace. Okay. And Kolmogorov took this as lead to define conditional expectation as a conditional projection onto a subspace, which I call S infinity here, which is defined by subalgebra of our algebra of random variables. So the algebra of random variables gave us this space here, L2, which was a completion in L2 now. Here we take as algebra the algebra generated by the observation, by the measurement. Okay, so all functions, and then we take the completion of that. Okay, so we take all functions of the measurement, and that's so all random variables which are functions of the measurement. And that's the space we project onto. And that's defined now that this conditioned expectation, which is written like this or like this, is an orthogonal projection from the whole space, which can be written like this, plus its orthogonal complement, onto this. So that's uniquely defined what this orthogonal projection is. Okay. Numerically, there's nothing nicer when orthogonal projections. They're numerically absolutely stable to compute. Okay. And we call this guy here, sometimes written like this, it's a projection. This is a conditional, sometimes one should say the preconditional expectation, because that's what it is before I have observed y. Okay. And it's a random variable because y is a random variable. But after observing y hat, it's not a random variable, then it's a number anymore. Okay, then it's just a real number. Okay, and it's after, you can say this is the post-conditioned. Post-conditional, I call this the conditioned expectation. So that's after the observation. Unfortunately, in the literature, everything's called conditional expectation, leading to confusion. Okay, so now we have a new expectation operator which replaces the old one, the one we started with. And this is why, because in physics, this is also called the state. And now this was describing the state of our knowledge before the observation. This describes the state of our knowledge after the observation. Yeah? So the state of our knowledge has changed, and so has the expectation we're going to use now. We know now y hat is true, and then we change all the probabilities and what expectations to reflect that. Good. So conditional expectation, again, is a orthogonal projection. So any random variable can be decomposed into the component which is in this infinity and in the orthogonal component. Okay, so that's this plus this. This is trivial to write this down. Okay, but the important thing is this is an orthogonal decomposition. And because it's orthogonal, I can use now Pythagoras, and now you see the conditional expectation. And conditioning is really comes. So it says the variance of this guy is the variance of this guy plus the variance of this guy. Okay. So you see that the variance, the L2 norm, will decrease, yeah, because this cannot be less than 0. It can be 0 or larger than 0. So if it's 0, then the update didn't change anything. We'll get new. The information was irrelevant for what we wanted to know about psi. Okay, and if it's non-zero, then there is some information, and this will decrease. So the variance will decrease. The probability distribution becomes sharper. Okay. Just now, how does this fit in? So if we take as algebra just the constants, okay, then it's the normal expectation. If we take the whole algebra, then it's the identity. Those are the two extreme cases of this conditional expectation sort of case. In our case, it's, as I said, the algebra generated by the measurement. It's not so simple as these two cases. Okay. And the question now becomes how to compute this guy. I said numerically it's very nice, it's an orthogonal projection, but the problem is how do you lay hands on your space and how do you compute this projection? So how do you build this filter? Okay. And we want XA to have all psi of XA to be correct. All the moments of XA should be correct as they're given by Bayes' theorem. So, yeah. Good. Now, because it's an orthogonal projection, we know, of course, it's minimizing the distance to the subspace. Okay, and this is where all these least square methods have their theoretical grounding in. Okay, so we know the argument which minimizes this over all random variables which are functions of y, we call this phi psi of y because it depends on psi. So this mapping, which is minimizer of this here, we call phi psi of y, and this is exactly the conditional expectation, but viewed as a function of y, of the observation. Okay. So this we call the conditional expectation map. And the subspace S infinity knows all the functions of y. This represents the available information. Okay. And the conditional expectation minimizes this square here. Okay. And this is called a loss function. Okay. And by minimizing this loss function, we get conditional expectation. By the way, there is many other loss functions which also produce the conditional expectation. They're called Bregman divergences. I will not go into that now. So for us, it's enough to have this one here. So it's minimizing the mean square error, or least squares problem, what we're doing here. Okay. But if we have to, typically, why would you want to do this? Why do you do an updating? Maybe because you want to make a decision, like what to set as controls for your error plane. Okay. Then you might want to have another loss function, actually, which reflects your losses, maybe. So the risks which are involved with taking this decision on that one. This goes into decisionary. We're not going to go with that. We'll stay with this loss function here. Okay. Now, if we take psi, the mapping psi, just to be the identity, then of course I get the conditional mean, okay, from this mapping. This whole procedure. If I take the tensor product of x with itself, okay, well, what do I get here? I get the correlation operator, and by subtracting this here, the conditional mean, I get the post-conditional covariance. So this is the covariance of the assimilated random variable. Okay, so I can get the mean, I can get covariance, I can get all the moments if I want to, if I have this operator Yeah, so this guy is the thing which we need to do all this. So how do we compute that? So just to say, if we had it, how do we do this? So we want to find a mapping here now, okay? So now there's different ways to build this mapping with a conditioning operator, a conditional expectation operator. It turns out that if you want to get this very accurately, it becomes very costly. We've seen this by looking at the Monte Carlo, Markov chain Monte Carlo, okay? So there's typically approximations taken as on how this is computed, okay? So there's something which I call the conditional expectation filter. We just make an update so that XA has the correct conditional expectation. For instance, for steering a plane, this would be the most important thing, because this is what you're going to use to set your new controls. Okay, you don't need a distribution, you just need one value to say, this is what I want to achieve. Okay, good. It turns out that this is already difficult because the correct conditional expectation is difficult to compute. Approximated by a linear version of this here, linear in y hat, we get what I call the Gauss-Markov-Kalman filter, which is linear in the difference here. Okay. Well, now this is a linear filter, but it doesn't have the correct covariance. So we can correct the covariance. It becomes the conditional expectation variance filter. Okay. Or we can make a better approximation of this guy here. Okay. So this is what you can try by doing conditional expectations of Kriging, but Kriging is actually a weaker form of this here, or doing artificial neural networks or whatever. They all try to compute this function here. We'll come to that later, okay, tomorrow probably. Good, so how does this simplest one, most of the filters are built on this, and the conditional expectation update. So we take the function to be computing the expectation of just to be the identity. So we want to compute this guy here, okay? And this is the argument which minimizes this here, okay? This is the function of y which comes out. And this is minimizing over all functions of y, okay? And if we have this operator, if we have this function, we can compute a new random variable xa, which has the correct posterior, okay? So this is called the MSE SE update or SE filter or whatever. Okay, because this is an orthogonal projection, I'm writing down again this orthogonal decomposition, and the x is decomposed in the component in here in blue and the component in here in red. The component in blue is in the subspace S infinity, this one which carries the information. That's the space of all functions of y. And this is just the rest. So that's trivial, but the important thing to write this equation down here, like you can write this down for any function, but the important thing is they are orthogonal. And the important thing is, as you see, so from this, I'm going to reconstruct my filter. I will say now the x, which is on here, this becomes my assimilated variable. Here I put the information y hat. I put a y hat in here, okay? And this guy I leave as it is. I don't know anything about this one here. So rearranging the terms gives me this here. So this is the forecast plus the innovation. And the information is the conditional expectation at y hat, which is just a constant, minus this random variable, okay? Now, if I compute the conditional expectation of this guy here, it turns out, because the conditional expectation of this is this, because this is a projection, doing a projection twice gives you the same thing. The conditional expectation of this here turns out to be the conditional expectation of this, and this is exactly this here. So this is the conditional mean. So this assimilated random variable has the correct conditional mean, okay? And now if we want to correct it even further, we have to correct the mean free part. This is this part here, the difference between this here and its mean. If we could change this, then we can get any kind of distribution we want to be better fitting to the Bayesian distribution, okay? Good, but now computing this exactly is already difficult, yeah? Because we have to minimize over all functions here. So now we're going to be simpler. We just take the linear or the affine functions, okay? Call it S1. And this will give us the minimum mean square estimator. So and this actually is a generalized version of the Gauss-Markov theorem, and it gives something which is a generalized Kalman filter. So by minimizing x over x1, we get a minimal k and b, The B is not important because it cancels in the update. Okay, cancels here. And the update then looks like this. And this K, this linear operator A, K is called the Kalman gain, and it's actually easy to compute what it is. It's this here. Yeah? Comes from minimizing the squares. And this is what we call the Gauss-Markov-Kalman filter. Okay, it operates on random variables. The normal or classical Kalman filter is a special case of it. It comes by taking the mean of this equation here. Okay, we'll come to that tomorrow, I think, how the correlation is. But for the time being, we just stay with this. So now we have two ways of doing it, doing the update. One was the Markov chain Monte Carlo. One is this GMK filter, GMKF. Okay. So what I'll show you now is some examples of that, and the rest is just going to be pictures of examples. So I think I have to finish now, but give me a few more minutes to show you the examples. Now we take, to show that it works for non-Gaussian random variables, okay, because the Kalman filter, unfortunately, only works for Gaussians very well. We take a very non-Gaussian random variable and a mathematical model which practically identity. So I want to identify this black distribution. That's the random variable I wanted to identify. Okay, the black guy. So I take 10 samples, okay, and do 10 updates with 10 samples, okay, and then I get, I think this is actually wrong. So the black guy is, the black guy is the data, the red guy is the data, and the green guy is the posterior. Okay, I think it's the wrong way around. And the colors here in these two pictures. So this is when I do 1,000 measurements, and you see how it picks up these peaks. So this is the red thing is the posterior, and it's very, very non-Gaussian. Whereas the prior, that's this blue distribution, which you see, that's a Gaussian distribution, a very, very wide Gaussian distribution. So it shows you that even this filter is so simple, this GMK filter, it can identify non-Gaussian random variables. Okay. Now we take a complicated model, something which is sometimes taken as a simple caricature of weather. This is the Lorentz 84 chaotic model. So the Lorentz model has three unknowns, three variables which model the state of the atmosphere. Okay, this actually comes from taking a big model of the atmosphere, doing an expansion in spherical harmonics, and taking the first three terms. Then you get a differential equation. U dot SF equals U, okay? And it turns out when certain parameters are put in a certain range, this system behaves chaotically, very unpredictable, okay? To show that it behaves, it run in the chaotic range. So it's very hard to predict, very hard to identify. That's what we're going to try to do here, okay? To show that we find the chaotic range, we've plotted here what's called a Poincaré cut. So we can think of this as a point in 3D, and this point moves around. And then at some point, at some time, it goes through the plane x equals 1. Every time it goes through the plane, it leaves a dot. If it goes from large x to small x, it leaves a blue dot and a red dot otherwise. Okay. And then if you do this a long time, you get this picture. So what we see here is a cut through something which is called a strange attractor. Okay. A thing which has not dimension 2 and not dimension 3, something in between. A fractal dimension. It's a fractal object. So it's just to show you that this is being run in the chaotic regime. Okay. And now we try to identify the state of the system. Okay. The time is still here in Earth days, because as I say, it's the model of the Earth's atmosphere. Okay. And we do observations every 10 days. Okay. Noisy observations. So we start with very rough estimates of what these are. So this gives you the prior probability distribution. The thick line is the mean. These are the 25% quantiles, and these are the, so there's 50% in between here, and these are the 95% quantiles. Okay. And here's a measurement, and you see how the distribution, the variance shrinks, becomes much narrower. Okay, and then it grows again here, especially you see the chaos lets it grow again, then observation, it shrinks again, and so on. And in the end, the posterior distribution is much narrower than we started with, and you can see this for the other variables. This is x, this is y, this is z. You can see this here too. Okay, so our probabilistic state, which is these 3 or 4 or 5 red curves, you see, is tracking the real state. okay, by measuring in intervals and updating the system. Okay. For another one, we can update also the parameters. So this is, I think, the parameters. So these are the 3 parameters which get updated. Okay. You see how the parameters go, and this is the state. Okay. So this is the state update, X, Y, and Z, and this is the parameter update. See how this becomes constant. We found the parameter. Okay, let's take another example. This is Cook's membrane under shear loading. That's why we have a little movie too, but I can't run it now. And you want to identify, in this case here, first the elastic constants by measuring the displacement at these points here and knowing what the shear loading is at the end. So it's clamped here and it has shear loading. It's a famous example to test finite elements. Okay, so when we do this, for the shear modulus, for instance, so we do this, of course, in the computer. We know what the truth is. So there's a blue cross where the truth is. So the prior is in green. Okay. If we have only one point, the prior doesn't become, sorry, the prior is in blue. So this is the prior. This very, very thin blue line here. If we have only one measuring point, well, we get closer, but not so close. In 10 and 21, you can see it becomes very narrow. So we can find what the shear modulus is. Okay. And now I wanted to show the movie on how to update this. This is an elastic plastic model, and you can find what is the yield stress. Okay, but unfortunately, I can't run the movie. I'll have to find a way of doing it. So it's another example, a plate with a hole. Okay. So it's 3 meshes shown. The green one was the initial mesh. And this is just to show what is the difference between putting in random variables in a model and then running it, and then taking the mean, the expected value, or first taking the expected value of the random variables and then running your model. This is what's normally done. I mean, every engineer knows that his models are uncertain. He takes the expected value of these parameters and then runs the model and then says, well, it's just going to vary a little bit about this. Here you can see where it varies a lot about it. So this labeled deterministic was done that way. So it was first the expected value was taken and then the model was run. And this is the stochastic model was run and then the expected value was taken. You see the blue and red one are quite different. Okay, good. And now you see, now the shear modulus is a field, a random field, which we want to update. So this is the error now shown on the finite element model, okay, in percent. Okay, so there's 18% error somewhere here. Okay, after the first update, you can see this shrinks down to somewhere in the 3% range. Okay, there's still in the corners here 6. And after the first update, the worst is 4%, and down here it's less than, it's around 2%. Okay, so the variance goes down from 20% to less than 2%. Okay, so this is how well we can approximate or identify a whole random field. Okay, so this is now in terms of probability densities. This was the prior, and the posterior turns out to be this. Okay, it happened to be 2.7 times 10 to the 3 or something. So 2.7 times 10 to the 4. Yeah, I think model for steel. Good. So this is how Bayesian updating works for this example. Now let's show me another example. This is upscaling. And upscaling, we do the following. We have a material which is so uncertain on small scales, we want to somehow average it on larger scales. This is analytically done with homogenization, okay? And then you find one value for these parameters, which you take as constants in space and compute with that. Now, if we have things where this homogenization, the analytical one doesn't work, there's different ways of doing it. One is to couple a micro model and a macro model at Gaussian scales by a FE squared. Some of them you have seen there, but that doesn't transfer scale transform information. That's why we use an approach. This was done together with Professor Ibrahim Begovic and his students, approach we call Miel. So this is a mesh and element technique. So, and with this, we allow stochastically heterogeneous material on the micro scale, and we want to decouple and we want to find the parameters on the macro scale, and we use Bayesian identification to identify macro scale. Okay, good. So that's an idea on how to do it. So we have either heterogeneous material on the microscale or random inclusions or something like that. We actually want one value, but one value is not good enough. This is what we want, actually a probability distribution of this one value. And this is what we're after here. And the probability distribution will describe the uncertainty which comes from the upscaling going onto the coarse scale. Okay, so here's a sort of a picture how this goes, where we compute the microscale. Okay, we can compute the macro scale, and then we compare these two. In this case, the stored and dissipated energies, and then we compare it, and then we use Bayes' rule to do the update. Okay, so how does this work? So this is one example, for instance, of such a microstructure, okay, and this meshing element. So this is a coarse mesh, and that's a fine mesh. You see every mesh here, every element here is subdivided into smaller ones here, okay? And it's actually a discrete model, a micro model, where we want to have a continuous macro model, okay? And discrete model has inclusions and little trusses in this case, connecting them when the trusses can break. And this is after deformation, it breaks here, and you can see the broken trusses. So this is identifying damage and cracking and things like that. You will see an example of that at the end. Okay, so let's take first this here. So we have a heterogeneous material on the fine scale, and we take the coarse scale element and put it under compression and shear and look at the energies and dissipation and do the updating. Okay, this is an update for the elastic constants. Okay, you see I become much sharper, and here too. Okay. Now, this is an update of the plastic properties, the yield stress and things like that. So this is a Drucker-Prager model. So the cohesion, the hardening modulus, whatever, all these guys get identified. Okay, and you can see after so and so many loading steps how this still changes and then settles down to the Weidelt curve is the final posterior after several steps. Okay. This is to see how the energy is captured. So because that's what we use, okay. So the black thing is the energy of the micro model, and this is the random variable of the macro model, okay. This is the prior, and this is the posterior. And this is for the hardening stored energy, and this is for the dissipation. Okay, now we take another example. So this is an example which was done by Emil Karavelic. This is an example of concrete. So there's Voronoi cells, and they're connected by Timoshenko beams. So there's a discrete model on the micro scale. We want now macro parameters for this here. Okay, first again the elastic constants. So this is the prior, and this is the likelihood of the observation, the green one, and the purpley one is the posterior. And actually here, both MCMC and the square root Gauss-Markov, so it's a version of the Gauss-Markov-Kalman filter were used. And you see they're practically on top of each other, okay? Now the same thing is for ultimate stress and fracture energy for fracture. And you see the final thing is the green one, okay? So before you start fracturing, nothing changes, but then it jumps to this here. So that's the identification of the fracture. So this will never get as narrow as it is for elastic parameters. There's too little time to go into that. Okay. So now this is an example where Markov chain Monte Carlo does not converge. So this is the prior, this is the likelihood, and so you see they're very far apart. And after thousands of steps, Markov chain Monte Carlo has only come to here. So this is where it will eventually converge. If you compute another 1,000 years, it will get somewhere there, but it hasn't yet, okay? So this is just to show you how the macro scale captures the mesoscale response, okay? So these are the bounds by the mesoscale, and this is the macro scale response, okay, of strain versus stress. Good, so I'm at the end now. So inverse problems are ill-posed when we view them in a deterministic manner. Viewing them in a Bayesian way makes them well-posed. And the Bayesian formulation basis conditioning. We have to see two ways of doing this, probability and expectation, okay? The probability version used MCMC, the other one used filters. And we've seen this works for non-Gaussian distributions, linear, nonlinear, highly nonlinear metals, and observation operators for ODEs, PDEs, and so on. So I'm finished here. Thank you very much. So I'm sorry I'm gone 15 minutes over the time. So it's time for lunch, but maybe There's a question from Bostian I see now. Can we do sequential updates for steady state model? Yes, Bostian, we can do steady state updates. And the following is the different times, so to speak, is different experiments. You have a steady state model, but you do different experiments. You change the loading, okay? So you're looking at steady state, but you do this experiment and then you do another experiment. So these are the different experiments, and there's different measurements and different updates. So this is sequentially updating for steady state models. The model itself doesn't have to have any dynamics. Are there any other questions? See, what changes in the sequential updates then is not necessarily the state. The state is just a function of the unknown parameters, but it's mainly the parameter which change from update to update. Because we do a different experiment, we learn new information about the parameters. Are there any other questions now? If not, you can think about them and then maybe pose them tomorrow morning. So if there's no more questions, I will say bye-bye to you, and we'll see each other tomorrow morning at 9 o'clock.